Hello there and welcome to Complana Studies, your personal student guide. This is lesson 3 in the Digital Logic Design series, the DLD series. And if you are new, don't forget to subscribe to our channel so that you're always updated and informed whenever we post something new on our channel. So also forget to share. Also don't forget to share the link. Don't forget to actually share the link with your friends, with those you know that are struggling with this subject, digital logic design. So with that out of the way, let's look into what we have for this video. Lesson 3, converting between base 2, 8, and 16. So we want to look at how to convert between base 2, 8, and 16 without involving base 10. Okay, fine. I want to convert from base 2 to base 8. Do I have to convert from base 2 to base 10 and then from base 10 to base 8? No, there's actually a simpler way to do this, to convert from base 2 to base 16 or from base 8 to base 2 or from base 8 to base 16. We'll be looking at that very shortly. So converting between base 2, 8, and 16 involves the use of a table like this one. It's very easy to write, it's very easy to form. Now in the table we have base 10 numbers. We don't use this part of the table actually, but it's just there to make sure that we can relate to the table because we normally count in base 10. So it helps you relate to the table. So remember that base 2 only has ones and zeros, base 8 only has numbers from 0 to 7, and base 16 has numbers from 0 all the way down to 15. So we know that 15 in base 10 is equivalent to F in base 16, and so that's why the table ends in 15. The entire table ends in 15 because that's the highest digit we have for base 16. Base 16 goes all the way to F. So that's 15 in base 10. Now if you look at base 2, you have two columns. You have two columns here. The 3-bit is used for base 8 conversions and the 4-bit is used for base 16 conversions. We'll employ this just shortly, but let's just get the basic concept. So you have 0 in base 10. 0 is still equal to 0 in base 2, it's still equal to 0 in base 8, and it is still equal to 0 in base 16. So in base 2, you notice that it's 0, 0, 0 that's written here, 3 bits, 0, 0, it still means 0, and even 0, 0, 0, 0 still means 0. So they still mean 0, there's nothing there, it's still 0. So you see 1 means 1 in base 2, 0, 0, 1, 3 bits, 0, 0, 1. Here you have 4 bits, 0, 0, 0, 1. Then you have 1 in base 8, 1 in base 16. Then when it gets to 2, you have 0, 1, 0 for base 2, 0, 1, 0, 1, 0 in 3 bits. Here you have 0, 0, 1, 0. They still mean the same thing. They are equal to each other. These mean 1, 0. It's just that I have 1 0 in front here and I have 2 zeros here. We'll see why this is. We'll see the reason for including these zeros in front when we solve examples. So it just continues in that way. And an important thing to note is that these are all mean the same thing, as in 7 in base 10 is equal to 1, 1, 1 in base 2 is equal to 7 in base 8 is equal to 7 in base 16. So they are all equivalent to each other. They want all the numbers on each row are equal to each other. So 2 in base 16 is 1, 0 in base 2, and so on. So the question is, how do I employ this table? How can I employ it in conversions? Let's go into that. We are converting between base 2, 8, and 16 between the three of them. So let's look at an example. Convert 4 to 7 in base 8. So I have 427 in base 8 and I want to convert that to a number in base 2. How do I do it? So we are not going to pass through, we are not passing through base 10 here. We're not going to convert this number to base 10 and then convert that number in base 10 to base 2. No. We are just going to go ahead and get the answer using this technique. So the first thing we're going to do is I'm going to write the numbers separately like this, 427. Now if you notice, 8 is equal to 2 to the power 3, right? 8 is equal to 2 to the power 3. This power here indicates the number of bits 3. Since 8 is just 2 to the power 3, each digit of an 8-bit number represents three digits in a 2-bit number. This is what I mean. 4 here is going to give you three digits of 2 bits, so it's 3 digits. 2 is going to give you 3 digits also, and 7 is going to give you 3 digits also. So each of these 8-bit digits gives you a 3-bit digit number. 3 bits. So we have to find the equivalent of 4 in base 2. The equivalent of 4 in base 2, but we have to keep it at 3 bits. So that's where the table comes in. That's where we employ this table. We need the equivalent of 4 in base 8. These are all the base 8 numbers from 0 to 7 and their equivalent base 2 numbers here. So we need 4. We're looking at 4 in base 8 and we see that it's 1, 0, 0. Again, the table is very easy to form. We just have to, okay, if you look at it from 0, 0, 0, you have 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. What's changing is that you can actually do it like this. You can write 4 zeros, 1, 2, 3, 4, and 4 ones, 1, 2, 3, 4. 4 zeros and 4 ones gives you 8, the 8 digits for base 8. And then you can now write 2 zeros, 2 ones, 2 zeros, and 2 ones. Then you write 0, 1, 0, 1, 0, 1, 0, 1. So these are the equivalent base 8. They equip the numbers in base 2 for the base 8 digits, what they represent in base 2. Then for base 16, you're going to write 8 zeros first. 1, 2, 3, 4, 5, 6, 7, 8 zeros and 8 ones. And 8 ones. Then you write 4 zeros, 4 ones, 4 zeros, and 4 ones. Then you write 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros. This is a pattern there. And then for the last digit, you just alternate between 0 and 1. 0, 1, 0, 1, 0, 1, 0, 1. So that will give you 16 separate numbers, 16 separate base 2 numbers, all in 4 bits. When you use that sequence, if you employ that sequence, you get everything here to give you 16 separate base 2 numbers. All will correspond to the base 16 digits, which go from 0 to 9, then A, B, C, D, E, and F. So it's very easy to form the table. Base 10 is just going from 0 to 15. Base 10 is just going from 0 to 15. That's it. Base 10 just goes from 0 to 15. Base 3, on the other hand, so the 3 bits for base 8, you still have to get that, and you still have to get the 4 bits for base 16. So back to our question. We're looking for the equivalent of 4 in base 2. So we're using the 3-bit section. Since we're converting from base 8, we're dealing with base 8. I want to convert that to base 2. So we're using the 3-bit section, which is this part here. And you see that 4 corresponds to 1, 0, 0. So I'm just going to write that down. 4 corresponds to 1, 0, 0. Those are the 3 bits for 4. For 2, let's check the corresponding 3 bits for 2. So 2 in base 8 corresponds to 010 in base 2. Zero 10 in base 2. And what about 7 in base 8? What does that correspond to? 7 in base 8 corresponds to 111. 3 bits for base 8, 111. 111. Now that I've gotten the corresponding digits, all I need to do is just join these together. So I take it as a single number in base 2. So this single number is 100, 010, 100, 111 in base 2. And I've done the conversion successfully. It's that easy to convert. So this is the equivalent of 427 in base 8. This is it in base 2. Each of the digits 4, 2, and 7 give you three bits. 4, 2, 7. Each digit is contributing its own to the number. So let's move on to our second example. It says we're converting 10111, 1041, 10111, 011, and then 5 ones, 11111 in base 2. We are going to convert that to a number in base 16. We want to convert this number to a number in base 16. If you look at it, 2 to power 4 is equal to 16, 4 bits. That's where the 4-bit relationship comes from, because 2 to power 4 is 16. So 4 bits. Now this is how you convert it. If you look at our previous example, you will notice that 3 bits correspond to 1 digit, right? 3 bits of the number in base 2 corresponds to 1 digit of the base 8 number. So that should give me an idea. Okay, 4 bits of the base 16 number should give me four bits of the base 2 number should give me a single digit of the base 16 number. So that means I have to group this number in groups of 4. I have to group it in groups of 4. The same way this number is in groups of 3. I've got to group this in groups of 4. Now, there's a rule here. You start grouping from the left. From the right. You group from the right towards the left. From the right towards the left. So I count 1, 2, 3, 4. I can draw a slash here. 1, 2, 3, 4. I draw another slash here. 1, 2, 3, 4. Another slash here, and 1, 2, 3, 4. So I've divided the entire base 2 number into groups of 4, starting from the right, going towards the left. The next step is to find the equivalent of these numbers in base 16. I've got to get their equivalents. It should just give me a single digit. They're going to give me single digits. I need to find those single digits. So we start first with 1111. We check the table for 1111. 1111 in base 16 is equivalent to F in base 16. So I know that I'm supposed to get F here. What about for 1001? Let's check for 1001. Here we have 1001, and that corresponds to 9 in base 16. 9 in base 16. Now we know what to write. 9. For 1101, 1101, we've got to check that table. 1101, this is 1100. So 1101 corresponds to D in base 16. So D in base 16. And finally 1011, 10111, we've got to check the equivalent in base 16. Here we are, 1011, that corresponds to B in base 16. B. And here we have our final answer, all in base 16. So you can just write it together now, BD9E in base 16. And are easily converted from base 2 to base 16 using this technique. Let's move over to the next example. Example 3, converts 1 1. So here we are converting 1 1 1 1, 4 ones, 0 1 1 1, 0 0 0 1 in base 2 to a number in base 8 this time around, to a number in base 8. Now we group in groups of what? So our target base is base 8, and we know that 2 to the power 3 is equal to 8. So of course we need 3 bits, right? 3 bits of 3. 3 bit numbers, 3 bits, groups of 3 there. So as usual, we start grouping from the right to the left. Start from your right and go towards the left. So 1 2 3 and make a slash. That's 3. 1 2 3 and make a slash again. 1 2 3 and make another slash, and 1 2 3. So I've separated this number in groups of 3, starting from the right. Now each one is going to give me a digit in base 8. I just need to find those base 8 digits, and that will be my answer. Let's get right into it. 0 0 0 0 1, what's the corresponding digit in base 8? 0 0 1, the corresponding digit in base 8 is 1. So I write 1, 1 1 0, 1 1 0 corresponds to 6 in base 8. Then we have 1 0 1. 1 0 1 corresponds to 5 in base 8. And finally 1 1 1. We have 1 1 1. 1 1 1 corresponds to 7 in base 8. 7. So my final answer is 7561, all in base 8. That was very easy, very simple to follow. Okay, so I think this is supposed to be F, not E. F, B, D, F. This is F, actually. not E. So it's BDF in base 16 because we got an F. I thought it was E because of the dash, but it's BDF, BD9F in base 16 for that example. So we're seeing how to convert from base 2 to base 16 and also to base 8. Let's see what our next example holds. Convert this to a number in base 16. So we have 1111, that's 4 ones, 01100, 10010.11, that's 6 ones, 111111 in base 2 to a number in base 16. So we want to get right into that, converting this number to a number in base 16. So what method do we're still going to apply a method, because we know that 2 to the power 4 is equal to 16. We're making groups of 4 because our target base is 16. So how do we start grouping? Now you take a look from here and then you start grouping from the left. This is the whole number part. This is the whole number part. So you just ignore the decimal part for a while. Focus on here. Group this using the grouping method we've been using. So 1, 2, 3, 4, I cut it here. 1, 2, 3, 4, I cut it here. 1, 2, 3, 4, I cut it here. Now, in this part here, I only have 1, 2 bits, not 4 bits. What do I do? Easy. Just add zeros to fit in, to make it 4. Add 2 zeros. If you notice, 0, 0, 1, 1, 1, all of it, it's still the same thing as the number itself. For instance, if I write 5, 0, 5 is the same thing as 5. 0, 0, 5 is still the same thing as 5. A million zeros before 5 is still the same thing as 5. So you can use that to fill in and get the total amount of bits you want, 4 bits. So I added 2 zeros to complete it, making it 4. Now I come over to the parts after the decimal point and I start grouping this time around from the left to the right. So from the left towards the right. Then for the whole number part, it's from the right towards the left. So from the left now towards the right. So I count 1, 2, 3, 4. I'm making groups of 4. So this is where the slash is there. 1, 2, 3, 4 slash. I'm grouping from the left towards my right. Now here 1, 2. It's not up to 4. What do I do? I add in 2 zeros at the end of the number, because if I have 1.5, 1.5 is the same thing as 1.50, the same thing as 1.500. So I can add any amount of zeros I want to add after the 5 and it will still be 1.5. So I use that and I add 2 zeros at the end to make it a complete group of 4. The final step is to get your digits. So each group of 4 is going to give me the corresponding 16-bit digit. Each group of 4 bits. We have a decimal point here, decimal point, then we have something here again, and we have something here again. And this will give me the entire number in base 16. So I just need to get the numbers. So what is 1100? You can check that out. 1100. 1100 is C in base 16. So I write a C, 1111, that is an F in base 16. So F in base 16, 0010, is 2 in base 16. 1001, is 9 in base 16. 1101, 1101, 1101 is D in base 16. D, and 0011 corresponds to 3 in base 16. 3. And here we have our base 16 number, and it's ready. So the number is 3D92.FC in base 16. Very easy to use. It's a very simple method of grouping and then converting. It's very easy. So we move on to the next example. And we have 2D7A.E in base 16 to a number in base 8. Now this is from base 16 to base 8. 2D7A.E in base 16 to a number in base 8. Let's get right into it. We know that we can draw a pattern here from base 8. We can go to base 2, and from base 2 we can move on to base 16. As easy as that. From base 8 to base 2 to base 16. Now we look at the number and we convert it to base 2. So it's in base 16 current. Okay, we can also move from base 16 and go to base 2, and then from base 2 to base 8 is like a circular pattern. You can move from base 16 to base 2 is like the intermediary base here. So base 16 to base 2, then from base 2 to base 8. So we're converting from base 16 to base 2, 4 bits. So each digit is going to give us 4 bits. This is giving us 4 bits. 1, 2, 3, 4. 1, 2, 3, 4. And the E, the decimal point here, 1, 2, 3, 4. So each is going to give us 4 digits. 4 bits. So what's 2? We've got to check the table. 2. Why is it the 4 bits for base 16? Because we're going to base 16. So 2 in base. Well, because we're converting from base 16 to base 2. So we're reading here. So 2 in base 16 is the same thing as 0, 0, 1, 0. So we have 0, 0, 1, 0 in base 2. Then D 1101 for D, 1101 for 7, 7 in base 16 gets you to 0111, 0111, 0111, A in base 16, A in base 16 gets you to 1010, 1010, and finally E in base 16 E in base 16, 1110, 1110. Now we have the number in base 2. So we're going to squeeze it together to get the full number 00. We can omit the zeros in front of the number because, as usual, 0, we said 005 is the same thing as 5, so we can actually drop the zeros in front. There's no need for these 2 zeros in front here. So we start from here, 101101, 0111, 1010, 1010, point, decimal point now comes in. We have 1110. We can omit the 0 here since it comes at the extreme at the decimal point, as in an example here. 1.500 is something as 1.5. So we can actually omit the 0 here and just write 111. This is base 2. Now our target base is base 8, so we're not done yet. We still need to group this in groups of 3 because we're going from base 2 to base 8. So groups of 3, that's what we're looking for. Now, as usual, we start from here. For the whole number part, we start from after, so before the decimal point, we start here from the right and move to the left. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. There's nothing there, so I'm going to add a 0 to make it 3. Just 1 0. We just need 1 0 to make complete our group of 3, and we have our groups of 3. Then for after the decimal point, we're looking from the left to the right. So 1, 2, 3, that's it. That's the only thing we have there. 1, 2, 3, and that's our group. So this is already a group of 3 on its own, so it can come forth. It can come. So this is going to give us, each of them gives us digits in base 8, which is our final answer. So what's our final answer? We need to check for 010. Well, when you check the table, we see that 010 is 2 once you look at the table. If you look at the table, 010 is actually 2. 010 is 2. The next is 110, which is 6. 101 is 5. 101. 101 is actually 5 from the table. 101 is 5, and we also see that 111 corresponds to 7. 010 of course is 2, and 111 is 7. So this is our final answer. 26572.7 in base 8 is the final answer. So we move on to our final example for this video. Convert 772.54 in base 8 to a number in base 16. So we got 772.54 in base 8. And we want to convert it to a number in base 16. So as usual, each digit in base 8, so we're going to pass through base 2 and then go from base 2 to base 16. So 2 to the power 3 is equal to 8, 3 bits. So I'm getting 3 bits from each of them. 1, 2, 3, 1, 2, 3, 1, 2, 3. The decimal point can come here. 1, 2, 3, and 1, 2, 3. 3 bits from each of them to form an entire number in base 2, and then convert this number to base 16. So 7 of 7, we have to check the base 8. 7 in base 8 would correspond to 111 in base 2. 111. 7 again corresponds to 111. We've already checked that. 2 corresponds to 010. Over time, you get used to this. 2 corresponds to 010, if you can see it there. And 5 corresponds to 101. We can see in the table that 5 in base 8 corresponds to 101. Then we have 4, which corresponds to 100. 4 actually corresponds to 100. When you look at it, 4 corresponds to 100. And we are ready to get the answer, not the final answer, but just the number in base 2. So 111, 6 ones, 111, 111, 010, 0.101, 0.101, 1. The zeros here can be omitted since they are just at the end of the number, and it's after the decimal point, so we can rewrite these zeros. So this is what we have in base 2. Now we convert to base 16 by grouping in groups of 4. 2 to the power 4 is 16, groups of 4 now. So from here, 1, 2, 3, 4. Make a mark after 4 bits. 1, 2, 3, 4. You make a mark again after 4 bits. And here we only have 1 bit. We need 4 bits, so I'm going to add in 3, not 1, not 2, but 3 zeros at the beginning. You can actually do that, 3 zeros to complete the group of 4. By adding 3 zeros, I've completed that group of 4, and then over here I just have a group of 4, right? 1, 2, 3, 4. That's what I need. So each one is going to give me a digit in base 16. The decimal point comes here. Each group is giving me a digit in base 16, giving us a final answer. So 0001, if you have guessed, is 1 in base 16. 1111 is F. We can verify that 1111 is F, and 0001 is 1 in base 16. We have 1010, that should be A. We can verify. One zero one zero is A in base 16. Then we have 1011. Which corresponds to B in base 16. B. And that gives us a final answer of 1FA point B in base 16. And we've converted from base 8 to base 16 by passing through base 2. So that brings us to the end of this video, at the end of this lesson, lesson 3. If you have liked what you've seen, if you've understood the video, understood what I explained, you can like the video, you can recommend the channel Complanar Studies for your friends so that they can participate and they can also benefit just the way as you're benefiting right now. And don't forget to make use of the comment section down below. Put in your comments, ask questions where you don't understand, and I'll be answering them on Fridays and Saturdays. And don't forget to subscribe to our channel. Of course, subscribe to Complanar Studies. It's a really good channel. And that's a wrap. That brings us to the end of this video. And have a nice day.